This video is about measurement error. In particular, it's an example where the measurement error is problematic and causes a bias in the regression slope estimate. So imagine an example where x is just a binary variable that's equal to 1 if an individual uses a Fitbit, otherwise x equals 0. And the outcome variable we're interested in is the minutes per week of this 3 MET, I think it stands for metabolic equivalent tasks, activity. It's a certain sort of level of activity that's a more vigorous exercise activity. That's what the Fitbit tries to measure when it measures your active minutes. And so following the textbook notation, y with the asterisk or y star is the true value, but we do not observe it for everybody, so it's a latent value. Instead, we observe y with no star, which is equal to the true y star, plus the measurement error m. That's what we observe. Now, imagine, I know the Fitbit is not perfect in reality, but imagine the Fitbit actually did perfectly record your minutes per week of 3 MET activity, so that there is 0 measurement error for the Fitbit users. So when x equals 1, meaning you have a Fitbit, m is just always equal to 0, and if m is 0, then the observed y is equal to the true latent y star. Now imagine for individuals without a Fitbit, when x equals 0, they don't really understand what this means. They just think if they're not completely still, they count that as activity. So if they, get up from the couch to walk to the refrigerator, they'll count that as part of their minutes. So what that means is, even if they have a very small number of true minutes, they think they're getting a lot. So in other words, the measurement error m is really big and positive. I'm going to put 2 greater than signs to indicate it's a lot bigger than 0. And so because of that, the minutes that they report and what we observe in the data is much larger than the true y star for those individuals. So if we try to think about this visually, I think that'll be the easiest thing to do. Imagine here's our x variable, 0, 1. So first we'll think about the true y star, and I'll represent those with open circles like this. So maybe this is what the Fitbit users are getting, and maybe it's actually pretty much the same for the non-Fitbit users. They're both like that. So these are the y star values, and then I'll draw x's. Oh, that's going to be confusing, sorry. For the y value. So for the Fitbit users, there's no measurement error. We observe the true value, so we observe that. But for the non-Fitbit users, they're reporting these huge numbers that are much larger than what they actually got. And so, maybe this person, we see something up here, and this person, we see something up here. This person reports something up here. This person reports something up here. So we see much larger values. So if we were able to observe the true y star, our regression slope would be about 0, because these open circle markers are all roughly the same height on average. But when we look at the observed y, which is the only thing we have in our data, we run a regression with our data set, we get this big negative slope, which sort of implies incorrectly that the Fitbit users, or using a Fitbit is associated with a much lower level of physical activity, which in this example, just by construction, is not true. So you can see this measurement error has a big negative correlation with x, and we get a big negative bias due to measurement error in our regression slope estimator.